Hi everyone, today we are going to see video solution for GATE Chemical Engineering 2015 mass transfer part. So first question, for a binary mixture of component A and B, Na and B denotes the total molar fluxes of component A and B respectively, and J and JB are the corresponding molar diffusive fluxes. Which of the following is true for equimolar countercurrent diffusion in the binary mixture? So we have a binary mixture that contains A and B. Now, what does this equimolar countercurrent diffusion means? The rate at which the A is getting diffused in B, with the same rate B is also getting diffused to A. And now we can write the total molar flux for Na, that is given as using the Fick's law, minus dAB, that is the diffusivity of A to B, dXA by dZ, plus Na plus Nb times the concentration of A or the fraction of A. Now this is the total molar flux, where this term denotes the diffusive flux, molar diffusive flux of A. So now in equimolar countercurrent diffusion we have the molar fluxes of A and B are same. The rate of molar flux of diffusion of A to B is same as from the molar flux of diffusion of B to A. So here and that is true for both cases, for the total molar flux as well as for the diffusive molar fluxes. So from here, from the equimolar countercurrent diffusion, we have Na plus Nb equals to 0 and Ja plus Jb equals to 0. It means that Na equals to minus of Nb, that we have already talk about the molar total molar flux diffusion of A from B is the rate will be same from B to A, and that is true for diffusive flux also. So for this we have D option will be correct. Now in the next question, a benzene is removed from air by absorption it in a non-volatile wash oil at 100 kilopascal in a countercurrent gas absorber. Gas flow rate is given, which includes the fraction vapor fraction of benzene is given, and the total flow rate of wash oil is also given. And we have been given that this solution is acting as an ideal solution. So first we will consider absorption column. So we have this absorption column where we have this flow as air plus benzene, where we have 98 air and 2 benzene mole per minute, that is already given, and where we have outlet where we have air plus benzene, and we are denoting this concentration as benzene as Y2 and the inlet as Y1. Similarly, we are denoting this as X1, which is the pure wash oil that does not contain any benzene wash oil, and the outlet is X2 which contains some benzene. Some benzene is extracted from the air. So this is wash oil contains some benzene. Now this is the absorption tower, and they are saying that this wash oil and this mixture. So somewhere here, if we consider here the wash oil plus benzene, this is acting as an ideal solution, and on the other part they are also considering that air plus benzene is an ideal gas. So we can apply those equations if wherever it is required. Now applying the operating condition for absorption column, we know as this as that absorption column Y2 minus Y1, which is the change in concentration in vapor for benzene, is equals to L by G m times of X2 minus X1, where this is the concentration in wash oil of the benzene, and this L denotes the liquid flow rate, this is liquid molar flow rate, G denotes the gas molar flow rate, and this M is the operating line slope. This is the equilibrium line, equilibrium constant we can say, which we will get here. We will get it is either given from the equilibrium data, or it is given as in the question it is stated that the wash oil and benzene is acting as the ideal solution. So we can generate at equilibrium, it follows the Raoult's law. So we will write Raoult's law as Y to P total. This is total pressure. Y is the friction of benzene in vapor, is X times of PB, that is the vapor pressure of B. So from here we can get Y equals to X. PB we have given of 50 and P total is given as 100 times of X. So it is basically Y equals to mx, where m is 0.5. So here now, what is absorption factor? This whole term is called as absorption factor, and we know L, we know G, and from the equilibrium data, from the using Raoult's law, we know M. So we can calculate the absorption factor. A will be L, that is L by G. We have already L has given 50, G is given as 100 divided by M. We have already found this 0.5. So from here we will get absorption factor as 1. Solving. So the correct answer for this will be 1, as the absorption factor for this process will be 1. Now in next question, a spherical naphthalene ball of 2 mm diameter is subliming very slowly in stagnant air at 25 degrees Celsius. So and the change in the size of the balloon is neglected and diffusivity is given, and they are asking the mass transfer coefficient of B. So we have a naphthalene ball whose diameter is given as 2 mm, and it is air is there which is stagnant. So this we have air. This is the, we can also understand physically. We also keep naphthalene balls in our cloth and everything to save it from foul smell. So we put naphthalene balls. So the diffusion is taking place, and this is the naphthalene ball, and we are considering that the naphthalene balls is not getting reduced. Only the thing is there is a diffusion occurring in the stagnant air. So now we will consider the naphthalene ball getting diffused in air, and we write the equation as flux, that is J, is equals to minus C minus DAB dCA by dZ plus the same term NA plus JA plus JB times XA. Now in this we have JB is 0 because it is told as a this is a stagnant, air is not moving. So now here we have flux as J, and we are also neglecting that total flux is J equals to minus, if we solve this we are denoting XA, and if we denote this, then it will comes as J equals to minus DAB by this will be 1 minus XA times dXA by dZ. So now here this is the total molar flux for naphthalene getting diffused in a stagnant air. Now here to calculate mass transfer coefficient, what mass transfer coefficient is that the total molar flow rate should be proportional to some K, that is times driving force, and this driving force is nothing but dXA, this whole term. So apart leaving this part, this is the term denoting the driving force, and this DAB by delta is denoting the mass transfer coefficient. So we have similarly if we match these two equations, we will get that the K value should be equals to minus DAB times delta Z. Now here the delta Z should be 1 mm, because we are considered 2 mm is the diameter. So from 1 mm 1 mm, this will be the distance of diffusion where the diffusion is taking place from center. So we will consider delta Z as 1 mm. So the molar flux will be DAB. So we have given 1.1 times divided by delta Z is 1 mm into 10 to the power minus 3. This will be our mass transfer coefficient, and this, if we calculate 1.1 into 10 power minus 3, it will approximately come 1.1 into 10 to power minus 3 meters per second. So from here, comparing this and this equation, we get B as approximately 1.1. So this will be the value of B. Now next question, a multi-stage counter-current liquid extractor is used to separate solute C from a binary mixture F of A and C using solvent B. Pure solvent B is recovered from raffinate R and distillate as shown in the figure, and a trinary diagram is given. So and we are asked that what the raffinate coming out from the extractor is represented. So first we will understand this diagram. So this diagram, this is the solute. We have this B as solvent, and we need to extract A. That is C is present in A. So this is carrier. So now, as you know, this part is a single phase part of ternary diagram. This part denotes the two phase. This is the equilibrium curve. Notes, and this F is the field. So from here, and the line F E is the operating line of extractor. Operating line, and from B, this line denotes the raffinate part. So this point is R1. This is E1, and the line joining R1 and E is called as tie line. So this it is a multi-stage. So how the separation is taking place? We have feed, we have operating line, then we have we are getting some extract. At equilibrium we are getting some extract, and corresponding to that extract we are getting some raffinate. Now again, this is the first stage. From again here, the next stage there will be a operating line, and similar to this, we this operating line, we have this part as E2. It is the extract part 2, and corresponding to this we will have R2. It is the raffinate. So this line will be a tie line, and from here this the line joining the B, that will intersect at R. Then again from here, next stage will start, and so the stages will be followed like this, and finally at this point this will be the R that is coming out. This raffinate is coming out from the extractor with the composition which has some extract. So see, this is the En. This is the extract phase after nth stage, and this is the raffinate after nth stage. So this U point is denoting the raffinate part coming out from the extractor. Now this P is denoting. Now if we further want to purify this, because at U the raffinate phase will contain our C, B and A, and we need to separate our solvent from this. So for that we use the distillation. So this part, this separation in our distillation, this part from U to P, we will apply distillation. So we started with the feed, we followed the stages, then R1, then R2, R likewise, and then nth stage we reached at Rn. Now from here to here, the further B is separated using distillation, and for P contains only A and C. So this is our main product, and B is separated. So this part is denoting the distillation part, and the other part is the multi-stage extraction is taking place. So from this we can clearly say that the raffinate coming out is denoted by the U. It is this raffinate part. So now in next question, a binary feed consisting 25 mole percent liquid and 75 mole is separated in a stage distillation column. A mole fraction of more volatile component in the distillate product is 0.9. So first we will write what are the parts that are given. So first is 25% liquid. It means fraction of liquid is given. So we can denote this as XL. So fraction of liquid is 0.25, that is already given, and fraction of vapor in feed is given as 0.75. Now also XD is given as they have provided 0.95, and the molar flow of distillate 50%. Also they have denoted D as 0.5 of F. And using McCabe-Thiele method can be used to analyze the column line and Q line intersecting. So we have, first we will draw this diagram where we have here Y, and this side we have X, and we have Y equals to X, one line, and this is the equilibrium curve operating to binary mixtures. And we have somewhere Q line is this, and we have a stripping line, as we know that this is the stripping line where this point is XD comma XD, and we have this Q, and this Q is intersecting at some part, this, and this point is denoted as 0.35 comma 0.5, and here we will have some this stripping line. Now, and they are asking the slope of stripping section, this line, the slope of this line. So first we will write the equations, like, now first we will find the Q. So what is the Q? By the definition we know that Q denotes the fraction of liquid present in the feed, and that is already given, that is 0.25. So Q is given. Now we will write the operating condition for enriching section, that is given as R upon R plus 1 times X plus XD times R plus 1. So from here we can calculate, we know Y. So this stripping section is also intersecting with Q line at 0.35 and 0.5. So we know these points. So we can put 0.5 equals to R divided by R plus 1 into X. X we know 0.35 plus XD also we know that is also that is already given in the question, 0.95 divided by R plus 1. So from here we can calculate reflux. So solving this equation, we will get the reflux value as 3. Now we get 3. Now what is reflux? Reflux is denoted, as we know already know from the mass balance, L by D. So what is L by D is we have some distillation column, we have from top product we have VM, and there is a condensate, then this is the distillate, and this is L, and this VM is nothing but L plus D. So we know L by D, so we can denote this L in terms of D as, so L we can denote as a 3D. So this VM will be actually 3D plus D, that is will be the 4D total VM. Now in stripping section we have a plate. Now if we apply the component mass balance and total mass balance, this plate, there will be a liquid that is coming out from enriching section, that we are denoting as L, and there is a liquid which is entering through feed. So this is the extra liquid which we are denoting by LF. This is LF, this is L, then we will have a vapor VM, and this extra vapor which is coming from the feed tray. So we will have this VM plus VF. So we have VM plus VF and L plus LF, and the slope of stripping section, as we know that from the operating equations, it will be V, that will be L by that will be L by D, that is the net liquid coming on this tray and net vapor leaving this tray, which is V by M, L by M, sorry. So this L total is nothing but LF plus net liquid that we are getting from top enriching section, divided by Vm. Vm is nothing but Vm plus Vf. That is, this vapor is minus Vf, because in bottom section this vapor which is rising, that vapor constitute of in feed, the vapor coming from feed as well as the vapor generating during the operation of column. So this Vm at the bottom section, this Vm will be Vm minus F, that is the total Vm. So Lf plus L upon Vm minus Vf. Now this we know L in terms of D, so we can denote this L as LF we can denote a fraction of liquid, that is already given 0.25, of feed, that is F, and F is we given as a 0.5% of D. It means that it is it is 2D plus, and this is given as L, this liquid part, that is already we have denoted as by 3D, that we calculated from here, divide by Vm. Not what is Vm? Vm nothing but L plus D. So D we already know what is L. L is 3 times of D minus Vf. What is Vf? Vf is the vapor that is coming, that is additionally adding due to feed. That is, some vapor is present in the feed, and that is 0.75 of feed, and feed we know in terms of distillate as 2D. So by solving this, we will get the ratio L by V as this ratio we are getting as 1.4. So the slope of the stripping section operating line will be 1.4. Now consider a steady state mass transfer process between well mixed liquid and vapor phase of a binary mixture comprising of component A and B. The mole fraction of component A in the bulk liquid XA and the bulk vapor YA are given. The mass transfer coefficient of component A in liquid and vapor phase are given, and the vapor liquid equilibrium curve is given as y star equals to this less than. So we are considering that this is the interface. Here gas is present and here pure liquid is present. Now in gas the fraction is given as 0.36. The y is given as which we denote as y, Ya. So Ya is given as 0.16, where Xa is given as 0.36, and the mass transfer coefficients, that is in liquid it is given as 0.1, and whereas in gas phase it is given as 0.05. That the units are consistent, so we are not writing units. So now KL is given. Now this is the interface part where we are denoting Xi and Yi, where Yi denotes the fraction of the component in vapor phase, and fraction of component in liquid phase is denoted as Xi. So here the equilibrium relation, because here the equilibrium will be established, and this equilibrium is defined by the relation that is already given as y equals to 2xi. So one relation we know this, and second relation we will get through mass balance. So here we will apply mass balance, that is we have mass transfer from gas side will be kg times, that is the mass transfer coefficient, into the driving force. Driving force is nothing but Yi minus Ya. That will be equals to mass transfer in liquid, that is KL, times Xi minus Xa. So this is the operating line. We have this Yi will be less and this Xi will be okay. Fine. Now this xi is nothing but, also this is mass negative, because the summation of this will be 0. So this is negative times of KL xi minus xl. Now this xi we can, this yi we can write as 2xi. So this and kg, so writing, putting all the values, we have kg as 0.05. So this is 0.05 times 2xi minus ya is given as 0.16, that will be equals to minus times of KL is given as 0.1 and xi is given xi is xi minus 0.36. Then we need to find the mole fraction of any liquid. So from here we can get xi, that is 0.1 of 1 xi minus 0.05 into 0.16 equals to minus of 0.1 xi plus 0.036. So solving here we will get xi as, that is coming out 0.22. So this will be the mole fraction of A in liquid at interface. Now next question, adsorption on activated carbon is used to reducing phenol concentration in wastewater from the given concentration to the required concentration, and the adsorption isotherm follows the Langmuir equation that operating temperature can be expressed as Q times some relation is given, Q equals to 0.025 concentration raised to power 1 by 3, where Q is denoted and C is denoted in terms of concentration, and we are asked to calculate the minimum amount of solid flow. So first we will consider this is where the adsorption packing is there, and this is a adsorption where we have it phenol flow from this side of the concentration 0.05 mole per liter and coming out as 0.08 mole per liter, and this is the adsorption that is following the equation as Q equals to 0.025 C raised to power 1 by 3. Now this is at equilibrium. This exit concentration is always at equilibrium. Now we are asked to calculate minimum amount of solid required per liter. So we are taking basis as 1 liter. So the amount of liquid we will find as, so net change in moles, that is Q, that is nothing but 0.04 minus 0.008 in 1 liter. This amount of moles are absorbed per x gram of solid, and that should be equals to the 0.025 times the concentration. Leaving concentration is at equilibrium, so we are considering the leaving concentration at equilibrium, and that is given, that is already given as 0.008 raised to power 1 by 3. So from here we can easily calculate how much solid is required, minimum solid is required. We are telling as minimum because we are considering the exit concentration at equilibrium. So the minimum solid required we can get here is x equals to as 6.32 grams. So this will be the minimum solid required for this operation. Now so this was all about the GAT Chemical Engineering 2015 mass transfer part. For more videos you can always subscribe this channel. Thank you.